Hello everybody and welcome to this A-Level Chemistry Head Start video. In this video we'll be taking a look at Organic Chemistry Part 1. So that's the part of organic chemistry that is common to people who studied triple science and also people that studied combined science. In Part 2 we will take a look at more of the triple only content. For now we're just looking at common content for combined and triple. Organic chemistry is the study of carbon-based compounds. And by far the most common carbon-based compounds is a family of chemicals called hydrocarbons. These are compounds made from hydrogen and carbon atoms only. So nothing else. If it's got some oxygen in, it's not a hydrocarbon. These hydrocarbons formed when plankton, which are tiny marine organisms, they died and were buried by sediment or mud and sand, and at high temperatures and high pressure over millions of years, they were converted into these hydrocarbons, which is a form of fossil fuel, as you'll remember. Carbon is very special in terms of its ability to form really long chains of atoms held together by covalent bonds to make molecules. Now, in something like crude oil, we have a range of different length chains all mixed together in a sample of crude oil that gets drilled up from under the ground or under the sea. And as it is, it's not very useful, so it needs to be separated. The length of the carbon chain in the hydrocarbon can vary greatly, with anything between 1 carbon in the molecule all the way up to 40 or more. One of the properties that this affects as the chain length grows is the boiling point of the hydrocarbon, and as a result this is the property that is used to separate hydrocarbons out from each other, to stop it from being a mixture of hydrocarbons, which isn't very useful, and we make it into groups of similar size carbon chains which are similar in terms of their properties and therefore have discernible uses. Now the process that we use is called fractional distillation. And at the beginning, crude oil is put into a furnace and it is heated to evaporate. And then the vapours enter a fractionating column, which is hotter at the bottom and cooler at the top. And what happens is the vapours rise up the column and cool down, and some of them condense and turn into a liquid and then get separated off from the side of the column, and they go off and have particular uses, whether that's diesel fuel, petrol, or refinery gas. That's the substance that drifts out of the top of the fractionating column without condensing. The boiling point of these molecules is so low, the column never gets cold enough to turn them into a liquid. Once we've completed fractional distillation for our hydrocarbon mixture, what we get is groups of alkanes of similar sizes. At GCSE level, you needed to be able to name the first 6 hydrocarbons, the first 6 alkanes. And that's why I'm showing these 6 on the screen now. We've got methane, ethane, propane, that's 1 carbon, 2 carbons, 3 carbons, and then butane, pentane, hexane, that's 4, 5, and 6. Each of these alkanes has their own formula, as I've shown here. We can work out what the formula will be of an alkane even if we've not drawn it by using the general formula for alkanes, which is CnH2n plus 2. What that means is if we went for nonane, which is C9, the number of hydrogen atoms that there will be is we double that 9 to get 18, and then we add 2, which gets us 20. So C9H20 is the formula of nonane. And from pent onwards, the naming convention makes a lot of sense. Pent means 5, hex means 6, and then we've got heptane, octane, nonane, decane, etc. And that then forms the beginning of the name, and then the end of the name tells us that we're working with an alkane. So these all end in ane because they are alkanes. Now, these alkane molecules all have something in common, which is that the bonds between the carbon atoms are always single bonds, and the carbon to hydrogen bonds are always single as well. And so alkanes are said to be saturated because all of the available bonds have been formed to different atoms. So every carbon atom has got 4 covalent bonds, and they are all connected to 4 different atoms. They might all be hydrogen or a mixture of hydrogen and carbon, but they're all different atoms. So it's not the same carbon atom that's got multiple bonds to it. Alkanes are not very reactive as a result of the fact that all of their bonds are single bonds. So that means that they aren't able to do things that alkenes can do, which we'll look at in a few minutes. Now, what they do well is burn. They burn to release quite a lot of energy, and so one of the most common uses for alkanes, the products of fractional distillation, is combustion, which again, we'll look at that later too. They do have some useful properties of a more physical nature rather than chemical reactions. So there's the boiling point, which, as we've just mentioned in fractional distillation, that boiling point increases as the carbon chain length increases, as does the viscosity. So that means its resistance to flowing, or sort of like the opposite of how runny something is, how viscous it is. That increases, that viscosity increases as chain length increases, as does volatility, which is how easily the chain evaporates, which does assist in the burning. So generally, the shorter chains are more volatile and they burn better as a result of that. Now, all of those properties are connected to attractive forces between the molecules, intermolecular forces, which I go into in a different video to do with covalent compounds. When we're working with organic molecules, we might need to name the molecule, propane for instance. We might need to show all of the bonds, as I did on the previous page. So this is called the displayed formula. Sometimes you might just go for what's called the molecular formula, and that's where you itemize each element that's present in a compound and you say how many times an atom of that element appears. So for propane there are 3 carbon atoms, so the molecular formula is simply C3H8. Sometimes you try and give a little bit more detail about how these atoms are organised in the molecule. And in that case, what you might use is something called structural formula, where you effectively list the elements as they appear. So we start with the carbon on the left. It's got 3 hydrogen atoms attached to it. And then we move on to the next carbon atom in the chain. That one's got 2 hydrogen atoms on it. And so we write CH2. And then the final carbon atom in the chain has also got 3 hydrogen atoms on it, so we put CH3 for that. So overall, we are saying that these atoms are appearing CH3, then CH2, then CH3. That is the structural formula, which is kind of partway between the molecular formula and the displayed formula. The reason that that's sometimes necessary and useful is because hydrocarbons are not always straight chains. They can exist as something called isomers. So if we were to take pentane as our starting point, that's C5H12. Now pentane is a linear molecule, and what I mean by that is it forms in a carbon chain, one carbon after the other. It's actually not linear, it's kind of like zigzag looking as a molecule, but we show it as a linear chain, 5 carbon atoms in a row with the 12 hydrogens around each of the carbons. However, when we write its formula as C5H12, if we were to draw that, we might actually draw different things, because there is a different way that we can organise those carbon atoms while still having the same number of carbon atoms and the same number of hydrogens. And the way that we can do that is have 4 carbon atoms in a row, and then the 5th carbon atom can come off one of the 2 middle carbon atoms in this chain. And we can't call this pentane anymore, even though it's got the same formula as pentane, because the longest carbon chain that we have is just 4 along the top. So that really is butane. And there is a carbon atom sticking out of the side of one of those carbons, and so we call that a methyl group when that's branching out to the side. And so this second molecule that I've drawn is actually called methyl butane. And so these are 2 different molecules, and that's what iso means. Iso means the same, and mer means parts. So they're made of the same parts, but we end up with a different molecule at the end. And so these are called chain isomers, where the chain, the kind of carbon skeleton it's sometimes called, is branched instead of being one straight chain. And another example is hexane, so 6 carbon atoms in a straight chain. Well, when we delve deeper into that, there are actually more potential isomers than just simply 2, because we could have a carbon chain of 5, and then we could put a methyl group on the very middle carbon, or we could put it on one of them just outside of the middle. And so that's already 3 isomers. And then there's a 4th isomer where actually you don't have a chain of 5, you have a chain of 4, and we've got 2 carbon chains to put into that branching situation. So we've got butane, but we've got 2 methyl groups sticking out from that chain. And so we would call this dimethyl butane. This is something you'll learn more about at A level, but I wanted to give you a little bit of a taster for it now. Very similar sounding and very similar looking to alkanes is a different family, a different homologous series, that's what we call it at A level, called the alkenes. So they're really similar because they are hydrocarbons, and that means there's no oxygen still or anything else like that, just carbon and hydrogen. But what we've got is we've got a double bond present in every single one of these molecules, which means they aren't saturated, we call them unsaturated. So the carbon atoms still have 4 bonds, whether that's 2 to a carbon and 1 to 2 hydrogen atoms sticking out from the side, but they definitely have somewhere in the molecule at least 1 double bond. So the first alkene that we have is ethene, and it's called that because it's because eth means 2, but it's ene because this is an unsaturated molecule, and we need to recognize that in the name. And then we move on to propene. Prop means 3, but it's an alkene because it's got that double bond. And then butene is the next. And we can work out what the formula of any alkene will be using its general formula, CnH2n. So that means once we know how many carbon we've got, let's say we've got 25 carbon atoms, we simply double that number of carbon atoms, and that's how many hydrogen atoms there will be. 50. That's the general formula for an alkene. Now, the presence of that double bond has huge effects on the usefulness of alkenes. They are incredibly reactive molecules. One of the things that they can be used for is to make polymers. When you turn an alkene into a polymer, for instance, ethene, you make polyethene. So that double bond allows a single ethene to join to thousands of other ethenes to make one long chain, and poly means many. So many ethenes are joined together to make polythene. That's not easy, it needs pressure, it needs a catalyst, but it is very useful once we've done that, because that is how we make our plastics, which we use for so many different things. Not just polythene for carrier bags, polypropylene for boxes, polystyrene for drinking cups and packaging and things like that. So hugely useful. I'll go into more details about alkene reactions in my Organic Chemistry 2 Head Start video. Similarly to alkanes, alkenes have got predictable physical properties in the exact same pattern that you would expect. For instance, they get more viscous the longer the chain becomes. If we return briefly to fractional distillation, where we learnt that we produce groups of hydrocarbons of similar chain length, the problem with that process actually comes about because we have a greater demand for the short chain hydrocarbons than the longer chain hydrocarbons, and that is rooted in the properties that these hydrocarbons have. The shorter hydrocarbons burn more easily and they flow more easily, and as a result, amongst other things, this makes them more useful fuels. So when we have a surplus of the long chain hydrocarbons, what we end up doing is processing them and converting them into shorter chain hydrocarbons, and that is the process called cracking. There are actually 2 different types of cracking. Both of them require a high temperature to carry out. One of them involves the use of steam. Unsurprisingly, this is called steam cracking. The other type of cracking is called catalytic cracking, and that uses a metal catalyst or a metal compound catalyst, which is typically aluminium oxide and silicon oxide combined together in something called zeolite. And when we carry out cracking, we end up with one of the simplest equations that you could ever ask for in chemistry. So we have a hydrocarbon here, such as decane, C10H22. When we carry out cracking, we always make that chain smaller. So we're always going to end up with 2 different molecules in the product, because another more general name for cracking is thermal decomposition, because we're using heat to break the molecule up. Typically, we will make an alkene during the cracking process, so C2H4, and then the other molecule will simply just be enough carbon and enough hydrogen to make sure this equation is balanced. So we need C8, because then 2 and 8 makes 10, and we need H18, because now the 18 and the 4 makes us the 22 that we had on the left-hand side. So this process of cracking has given us shorter chain alkanes and given us one of these really reactive alkenes. Something additional that alkanes and alkenes share is that they both burn in combustion reactions. And so what that means is they will react with oxygen and they will turn into oxides. The carbon from the hydrocarbon turns into carbon dioxide and the hydrogen from the hydrocarbon turns into water. So during the burning process, a lot of energy is produced, but in addition to that, we produce carbon dioxide and water. And you need to be able to balance equations like this. And for alkanes, it's always easier when there is an odd number of carbon atoms present. So if we just take a look at three of these, we've got methane, ethane, and propane. What you can see with methane is that there's only one carbon in the methane, so we'll only make one carbon dioxide. There are two hydrogen atoms in water, and so that means that when we're balancing this equation, we need to put a 2 in front of the water because that gets us 4 hydrogen on the right hand side. And so now we've got 2 oxygen in the water, we've got 2 oxygen in the carbon dioxide, so 4 oxygen on the right hand side. That means we need 2 O2s on the left hand side to balance that equation. Ethane is tougher because in ethane there's 2 carbon, which means 2 CO2, 6 hydrogen, which means 3 H2O. Now when we add up our oxygen, we find that we've got 3 oxygen in the 3 H2O, 4 oxygen in the 2 CO2, which makes 7 oxygen overall, which means we're tempted to put a 3.5 in front of the O2, which is actually okay at A level, but it doesn't sit well with some people. When you're faced with a situation like this, what we're thinking is, well, how can we get rid of that fraction? So we've got 3.5, or 7 over 2, and the way to get rid of that fraction is to turn everything twice as big. So we end up with 2 ethane, 7 O2s, 4 CO2, and 6 H2O. Then when we get back to propane, everything's easier again because we've got 3 CO2 and we've got 4 H2O, and so that means we need 10 oxygen on the left, so we need 5 O2. Alkenes burn in a similar way to alkanes, so you could be required to balance an equation, for instance the one that I've got here, but the thing that is worth noting is that they do tend to burn with a slightly sootier flame than alkanes. In other words, it looks a little bit more yellow flame, like the safety flame in a Bunsen burner, and that's because the reduction in the number of hydrogen atoms means that there is a greater proportion of carbon compared to the hydrogen, and that is typical in terms of producing a sootier flame. The significance of that sooty flame is that the hydrocarbon isn't burning properly. We're getting incomplete combustion caused by a shortage of oxygen. So in complete combustion, we always make carbon dioxide and water, whereas if the hydrocarbon isn't burning properly, we might produce carbon monoxide, which contains half as many oxygen as CO2 does. Or we might even just make soot, carbon particulates, and that obviously doesn't contain any oxygen at all. And so we can see from these balanced equations for incomplete combustion, all for the same hydrocarbon, that what we've got is a decreasing amount of oxygen each time on the left on the reactants, leading to a production of a carbon compound in the product that contains less oxygen due to that deficiency in the first place. This can obviously cause huge problems because carbon monoxide is a poisonous gas and carbon particulates can contribute to global dimming and give people exacerbated asthma, causing respiratory problems as a result of breathing in those particulates. Another problem that can occur during the combustion process is small amounts of sulfur that are contained in the hydrocarbon structure, in amongst those hydrocarbons, can also react with oxygen at these high temperatures and produce sulfur dioxide. Sulfur dioxide itself isn't a pleasant gas to breathe in, but part of that problem is that the sulfur dioxide will rise up into the atmosphere and produce acid rain once it dissolves in the moisture in the air. And obviously when acid rain happens, we can lead to corrosion of buildings and damage to habitats, whether that's lakes and the marine organisms that live in the lakes. So acid rain can cause huge problems. As a result of that, we try to remove the sulfur from the fuel either before it's burnt, or we try and remove the sulfur dioxide from the fuel once it's burnt and kind of desulfurize the fumes, the gases that get produced as a result of the combustion process. Because, as I say, sulfur dioxide can also cause respiratory problems and make people's asthma worse. And the final problem that can be caused from burning fuels is that the high temperatures produced by the exothermic reactions as this combustion occurs can lead to nitrogen just from the atmosphere reacting with some of the oxygen in the atmosphere and producing oxides of nitrogen. This happens in particular in things like car engines, where we burn the hydrocarbons present in the petrol fraction of alkanes. And when this happens, out of the car exhaust comes these oxides of nitrogen, which can also dissolve in water in the air and also contribute to acid rain and causing all those problems that I've already mentioned. And so as a result of that, car engines are typically fitted with catalytic converters, which reduce the oxides being produced. And what they will do is they will try to react these gases, turn them into something new, and then vent the less harmful gases out of the car exhaust rather than these oxides of nitrogen. And the catalytic converters also process carbon monoxide that might be produced through incomplete combustion in the car engine as well, actually turning it into carbon dioxide, which obviously we know isn't great because that contributes to the global warming and the greenhouse effect. But clearly that is far preferable compared to releasing poisonous gases out of the exhaust of cars. So that's why legally all cars have to be fitted with catalytic converters. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.